So, hello everyone. Very good afternoon or very good evening. Welcome to today's live interactive session or live discussion session on geology and soil mechanics. Today is the fifth week of our course, and today we'll be discussing whatever was taught to you on the fifth week lectures. In the past week, in the past week, we have discussed and solved some problems from variability and seepage. So we are going to continue with that in the today's session. So let us start slowly, steadily. We will first discuss some of the main concepts from this topic, and then we will solve some basic easy problems. So let us see what we have. So, so we'd also discussed about this in the previous class. So we'll continue with that. So what are flow nets? So flow nets are nothing but the solution of the Laplace equation, right? So flow net is nothing but the solution of the Laplace equation, which the flow net consists mainly of the flow lines and the equipotential line. The flow lines and the equipotential line, both of them are called together the flow net. And these lines, the flow lines and the equipotential lines, are generally are always orthogonal to each other. That is, they are perpendicular to each other, and yeah. So let us see how we can decide and how we'll be drawing a flow net. Okay. So here you can see we have a problem that is given to here, where we have a sheet pile. Okay, sheet pile, and we have some upstream head, we have some downstream head. So as upstream head is higher than downstream head, obviously there will be some flow of water. So this flow or the seepage of water through the soil can be described using the flow lines. Okay, so how do you draw the flow net? So several trials are actually needed to draw a flow net. So you need to roughly draw first, then you have to see that all the criteria such as the orthogonality criteria, then the square criteria, the squarity of the elements, those things are maintained, right? You can see AB and DE are the equipotential line. So which is AB? AB is this top line and this line D. These are the equipotential line. So in the AB, the head is all throughout the line AB. At all the points on the line AB, the head is constant, right? That is H1. So we call it a equipotential line. And similarly for the line DE, the head at all the points of the line is H2. So again, that is an equipotential line. So all the flow lines intersect them at right angle. So all the flow lines should intersect these at right angles. Okay. FG is a flow line. So this bottommost, this boundary, this is the impervious layer. Okay, this is the impervious layer, and above that interfacial line is that interface that is there. That is the what? That is the flow line. Again, ACD is also a flow line. So what is ACD? This ACD. So this is also a flow line. Okay, this is also a flow line. The equipotential line intersects FG and ACD at right angles. So FG means here. These are the equipotential lines. Dotted lines are the equipotential lines, and obviously this has to intersect these lines at the right angle. Okay, also here. Okay. Flow channel is the strip between any two adjacent. So that we also discussed in the previous session. And the flow channel is nothing but this strip. Okay, this strip is the like this. These strips are the flow channel. The area between any two adjacent flow lines is called the flow channel. Okay. Just a second. Actually, I'm not keeping that well. I have very cold and cough, so it's very difficult to actually take class like this. So pardon me for any mistake if I do any mistakes, or if you're not able to understand anything, or if I'm not clear. So please pardon me for that. If you have any doubt, please feel free to write to me over the email, and I will try my best to help you. Okay, so now if you see, so as I said, this is a flow line, say, and this is a flow line. Okay, and these dotted lines are the equipotential lines. So at at this equipotential line, the head is H1. At this equipotential line, the head is H2, and so on. Right. So what is the hydraulic gradient for a flow from here to here? It's nothing but H1 minus H2 by L1. So L1 is this length. L1, right? And what? And what is the area? What is the area of flow? Area is so L1 into 1. Okay, these things also already we discussed in the previous class. Still, I'm just repeating it. As per Darcy's law, delta Q is nothing but K is the hydraulic conductivity. Right? So we have K H2 minus 2. Also, you can write L2. So you can write like this. Okay, since these are square elements, since it's a square element, the dimensions are same. Now H2 minus H2 is equal to H2 minus H3 is equal to dot dot dot. You can write is at H by total head difference. Total head loss is by number of potential drops. Like this you can write. Therefore, delta Q, that is the flow through each channel, is this. This is the flow through one channel. Now, if we have NF as the number of flow channels, then what? Then total Q is Q into NF. So we have KH I and D. Right? You have this. Okay. Okay. This is for square. When the square, we have the square elements. Okay, square elements. Right. Now, flow nets in anisotropic soil. So, what do you mean by anisotropic soil? So, anisotropic soil means the coefficient of permeability or the hydraulic conductivity is different in the x direction and z direction. In both these directions, the hydraulic conductivity is different. Okay, so that is the anisotropic behavior of the soil. Okay, in the vertical and the horizontal direction, the coefficient of permeability or the hydraulic conductivity are different. In that case, what happens? The flow lines and equipotential lines are not perpendicular to each other. So what happens? If kx and kz are different, then we have the Laplace equation is like this. So to to make the element square and to make the these two lines to draw in such a way that these two lines become perpendicular, what we have to do is we have to do some substitution. So you can write like this, right? So okay, so finally we can write this as the x dash square plus square equal to 0, where x dash is az by kx into x. So the horizontal coordinate, okay, we need to scale by this. Okay, only then we will be able to get square elements and we will be able to get orthogonal flow lines and equipotential lines. Okay, so how to draw, finally how to draw? So this is how we have to draw. Okay. So adopt a vertical scale for drawing the flow net. Then choose a horizontal scale such that horizontal scale is kz by kx times the vertical scale. Okay. Construct the flow nets by regular procedure, and then the rate of seepage per unit length is given by okay, in place of k, in place of k, it gets replaced by this kz kx. Okay. Okay, so next we have the flow net for determining uplift pressure under a hydraulic structure. So if you have a hydraulic structure, any hydraulic structure, obviously what happens to when if it is water is there on one side or water, we have seepage happening. So the seepage of water produces a uplift pressure, okay, upward pressure that acts upward, okay, just tries to uplift the hydraulic structure, okay, that is known as the uplift pressure. So how can we find the uplift pressure from the flow net? So that we will see. So if the coefficient of permeability is different in both x and y direction, flow lines and equipotential lines are not perpendicular to each other. And if they are If they are equal, then the flow lines and flow nets will be perpendicular to each other. Okay, now let us see this. So here we have a hydraulic structure. Okay, so we have a head here, 7 meter head. Okay, and 2 meter is submerged into the soil. That is, it's embedded into the soil. Okay, 2 meters embedded into the soil, and 7 meter we have upstream height. We have the water on the upstream height. So this is the flow line, and these are the equipotential lines. Okay, these are the equipotential lines. Now, can you tell me what are the number of total number of equipotential, total number of drops, head drops, or total number of drops that are happening here? Can you tell me that what are the total number of drops that are happening? What are the total number of drops? So see, from here to here, one drop, two drop, three drop, four drop, five drop, six drop, seven drop. So total number of drops are seven. The total head is 7 meters, right? So we have H by ND for in each drop, the head loss is 7 by 7, that is 1 meter. So in each drop, each potential drop, 1 meter of head is actually lost, or 1 meter head drops. Now there are total seven drops. So for each drop, the head loss is H by 7. And H here, H is nothing but also 7, so 1. 7 by 7, 1. Now at A, uplift pressure is what? The total head. So uplift pressure is what? Uplift pressure is nothing but the pressure head times the pressure head times the gamma W. That is the unit weight of water. That gives us the uplifted. Uplift pressure is nothing but the total the pressure head times the uh, unit weight of water. The pressure head times the unit weight of water gives us the uplift pressure. Okay. Okay. So uplift pressure is what? Pressure head times gamma W. Pressure head is what? Pressure head is total head minus elevation head. Okay, times gamma W. So total head minus elevation will give us the pressure. The pressure head times gamma W will give us the uplift. Now see. Now at the point. So if we take this as the datum, we take this level, the ground level as the datum. Ground level is the datum. Okay, we take the ground level as the datum. Then our total head is what? Total head is 7. Okay, total head is 7. At A, right? Just a second. Yeah, the total head. Okay, so total head minus elevation head. Now, how will I get the total head at any point? Total head will be nothing but the total head is nothing but, so forget about this. Okay, total head is nothing but the total head at any point is the initial head. Total head at any point, initial head minus number of drops times head lost in each drop. Okay, but initial total head is nothing but initial head minus number of drops times head lost in each drop. Okay, so if you want to write the uplift pressure at A, so what is my total head? So total head at this level is 7. Okay, I need to find this level at here at A point. What is the total head? So if at this point, the total head at this level, at this equipotential, if at this equipotential line, my total head is 7, That is initial head is 7. That is the initial head. Now from here to here, when I come, one number of drops is happening. So the A is here. So from here to here, I have one number of drops. I come to this equipotential line. A falls in this equipotential line, right? Our A falls in this equipotential line. So from here to here, when I come, there is one drop. So in one drop, initial it is 7. So from 7, how much drop is there? One drop is there. One drop time head lost in each drop is what? H by 7, that is again 1. Okay, this gives me the total head minus the elevation head. So this I have taken. So this ground level I have taken as the data. So it's 2 meter below that. So minus 2. Minus 2 is the elevation head. So this will give me my pressure head. So times W, gamma W is my what is my so 8 into gamma W is my uplift pressure at A. Similarly, if I want to write the uplift pressure at F, so what is was the initial head? Initial was 7. So from 7 loss, it's happening. So how many drops till we reach the point F? How many drops? 1 drop, 2 drop, 3 drop, 4 drop, 5 drop, 6 drop. So here F is here. So 6 drops on the sixth equipotential line. We have the F point. So 6 drops we have to take. That has to undergo 6 drops. So 6 minus 6 times what? The head lost in each drop. Head lost in each drop. It is 1. This is my total head. Minus 2 again. Isn't it? So this will come out as what? 7 minus 6 is 1, or 1 plus 2 is 3. Okay, so like this we need to do. We need to find the uplift pressure. So we will solve one problem today. In that case, it will get clear to you more. Okay, you understood, right? So total head minus elevation head. So our total head at any point, say at any point X or at any point A, if you want to find the uplift pressure, then we need to first deduct the total. We need to deduct the elevation head from the total elevation head at point A, from the total head at point A, times the gamma W will give us the pressure, uplift pressure. Okay. So we need to find to find the uplift pressure at any point A, we need to we need to find the pressure head at that point A. Fine. Again, I will repeat. To find out the uplift pressure at any point A, to find out the uplift pressure at any point A, to find out the uplift pressure at any point A, we need to first find out the pressure head at that point A. Okay, so uplift pressure at that point, any point A, is equal to the pressure head at that point A times the gamma W. Now the pressure head at that point A is the total head at that point minus the elevation head at that point, that particular point. Okay, pressure head is equal to nothing but the total head at that point minus the elevation head at that point. Now, how to get the total head? So total head is nothing but the head there is there initially, that head is there. From there, from that initial head, if I minus the number of drops, times the head lost in each drops, I will get a total head in that point. So, I do that I get a total head at that point minus deduct the elevation head, I get the pressure head. Then I multiply it by gamma W, it gives me the uplift pressure. So next we have the seepage through an earthen dam. So how can we calculate the seepage loss through an earthen dam? So for that, what we need to do? For that, we need to first construct this phreatic line. So phreatic line is nothing but the line above which there is atmospheric pressure that is acting. Okay, that is the phreatic line. Okay, above that line we have the atmospheric pressure. Now this phreatic line, this A dash BC is a parabolic. Okay, so it's given that this A dash BC, this line is parabolic. So what we need to do, we need to first estimate ABC. This ABC curve I need to estimate first. Then I need to find the A dash point. Now, if I find the A dash point, then I can get A dash BC. Now, A dash BC is nothing but my phreatic line. Okay, so not sorry. ABC is the original phreatic line. From ABC, I need to get the A dash BC. A dash BC is parabolic. Now, then by using the equations of parabola, we can calculate the seepage loss. Okay, so we will have use of taking use of the equation of parabola. Okay, so now as I said, it is assumed that A dash BC is parabolic. The slope of the phreatic line can be assumed as I, and it is equal to dz by dx. That is this by this. The tangent of this point, tangent of this phreatic line at the point is not. It's considered as the slope of the phreatic line. Okay, I. Okay. Now, what we do, we consider this triangle CDE. Okay, it consider this triangle CDE. Now, the rate of seepage perpendicular to the cross section, this cross section, okay, this cross section can be written as Q is KIA, where A is the area. Now, I is what? I is dz by dx, right? So, it can be written as tan alpha. This alpha, you have alpha is nothing but this toe angle. Okay, this angle at the downstream side, this angle is alpha. Now, area is what? CE, this CE cross sectional area, the CE times 1. So, this out of direction we are considering 1. So, CE times 1. This can be also written as L sine alpha. Now, the rate of seepage per unit length to them through the section BF. Now, this is in at any section BF, we need to find the rate of seepage. So, what will be that? So, Q is KIA. Ki can be written dz by dx into z into 1. That is the height at that point. Here, okay. So this is z height. This is the z height. So kz dz by dx. Now what I can do now? Now, so as there is continuity in the flow, I can equate these two equations. Now if I integrate this from sine alpha h kz dz L to L cos alpha d a L tan alpha dx will get ls d by cos alpha minus root over d square cos square alpha minus h square by sin square alpha. Okay, so L I can find out. Now if I know the L, if I have calculated the L, I can find out my Q. So Q will be AL tan alpha sine alpha. So alpha I know it will be the downstream angle, downstream slope angle. A I know, L I know. So I can calculate the flow like this. Okay. Now the steps to calculate Q, obtain alpha, calculate delta and 0.3 delta to get A dash, calculate D. So what is D? D is this from here to here. This is D. Okay. We need D, right? Calculate D, then we calculate the L from the equation that we just derived, and then from L we calculate Q. Okay, this is how we need to calculate the flow. Okay. Just a second. Huh? Okay, so when alpha is greater than 30 degrees, I is dz by dx. So this I equal to dz by dx is not valid. It's not valid. So Casagrande suggested that I is equal to dz by ds at that time. So this is dz, this is dx, and this is dz. So dz by ds is suggested. So I'm not repeating the derivation again. This derivation is also discussed in the class. In that case, how to calculate the flow. Okay. Now let us continue. Next, we have the in situ stresses. Okay, in situ stresses. So we have this soil mass. Okay, soil mass. We have the soil grains. Okay, we have the soil grains. Okay, this is the water head. Okay, then this is the total depth at any level A from the top. Okay, the cross sectional area is A bar. Right, all this we have. Now how to write the total stress? Total stress at A or at this level, at this point A, at this level is equal to H into gamma W, right? So the H into gamma W plus H is this, right? This is H into gamma W, unit weight of water plus HA minus H into gamma saturated. What is the H gamma saturated is the saturated unit weight of the soil. Okay, all right. Right. So this is why total stress. Now, the total stress comprises of two parts. One is my neutral stress, or it's called the pore water pressure. The other is my effective stress. Okay. Now, what is the neutral stress or pore water pressure? So, if the soil is completely saturated by water, we have water in the pores. Okay, in the spaces between the soil grains, we have water. So, as you know, water exerts equal Pascal's law, right? So, from Pascal's law, we know that water exerts equal pressure in all the directions. So, it pressures an equal amount of direction all around. Okay, that's why it's known as a neutral state, because it exerts equal pressure in all the directions. Okay, so one component of the total stress is this neutral stress from the pore water pressure. And the other part is the effective stress. Now, what is effective stress? Effective stress is nothing but the actual stress that is transferred at the grain to grain contact. So, when you apply soil a load into a soil, the load is transferred. How? A load is actually taken by the soil skeleton. Right, the load is actually taken by the soil skeleton, and the soil skeleton transfers this load by transferring the load at the grain to grain contact points, right? So that is the effective stress. Effective stress is nothing but, if you sum up at any level, if you sum up the contact forces between two soil grains, that stress will give you the effective stress. Okay, if you sum up the stresses, contact stresses between the two grains, and that stress will give you the effective stress. Okay, so at any level, there are many soil grains in contact. So if you sum up all the stresses, contact stresses at that level of all the pairs of grain, all the contact stresses, intercellular contact stresses, that will give us the effective stress. Effective stress is the stress that means actually that is taken by the soil skeleton. Now, so you can see this dotted line. So here we have one grain, here we have one more grain, one more grain. At these points, there is some contact. The loads are transferred at this contact point, isn't it? So if I just draw the top layer of these grains, it will be something like this, right? These things. Now these are the contact forces. So you can say contact forces that is there. These are the contact forces that are there. Now, so this is the P1. These are contact force at one point. So obviously this has two components, vertical and horizontal. Effective stress is nothing but if you sum of these, okay, sum of all these all these vertical component of all these contact forces, you sum of the vertical component of all these component forces divided by the area. Okay, this total cross section area, that will give me the effective stress. Okay, that will give me the effective stress. Okay. So total stress, some amount of the total stress is taken by the soil solids at their contact, and the other portion is carried by the water. Okay. Sum of the vertical portion of the contact forces of the soil solids divided by the cross-sectional area of the soil mass gives the effective. Okay. Sum of the vertical component of the contact forces of the soil solids divided by the cross-sectional area of the soil mass gives the effective. We apply load. As soon as you apply load, some amount of load is taken by the water part and some amount of load is taken by the intergranular, the soil skeleton. Okay. So mainly this load transfer or the strength of the soil is coming from this effective stress part. Okay. So we'll see later as we progress in the courses for describing every strength criteria of the soil. For everything, we use the effective stress because effective stress is the actual defines the actual property of the soil structure. Right. So right. Okay. Understand, right? So now if small as is the cross-sectional area occupied by soil to solid contact, soil solid to solid contact, then how much area is water taking? A bar minus AS. Excuse me. Right? So if small as is the contact area occupied by the solid to solid contact, then the water occupies the area capital A bar minus the AS, the cross-sectional area minus AS, right? Also, so right, now this into A bar, total stress times A bar, we can write as effective stress times A bar plus the poured water pressure times A bar minus AS, right? Now, second right is plus U A bar minus AS by A bar, right? So, equal to plus 1 minus AS by A bar. Now, what is AS? AS is the sum of the what? Total grain to grain product, these areas, okay? So, these areas, okay? Okay, these areas. So, these areas are very small compared to A bar. So, this tends to 0. Okay, since the denominator is very large compared to AS, this is 0. Okay, so finally we have total stress equal to effective stress plus water pressure. Okay. So this is in the case of fully treated soil. There are no air words. There are no air words. So then this is the key. Now let us come to this. Now now at a point, what will be the pore water pressure? Pore water pressure is HA times gamma W. What is the total stress? H into gamma W plus HA minus H by our Z. HA minus U is H into gamma W plus HA minus H gamma Z minus HA times gamma W. Okay, so this will come out as HA minus H gamma Z minus gamma W. So we have the effective stress at HA minus H times gamma submerged. Okay, gamma submerged. This is my pore water pressure. This is my total stress, and total stress minus pore water pressure, we know it's the effective stress. So get the effective stress is this HA minus H into gamma sub. This height times gamma submerged. Okay, this height times gamma submerged. Okay, okay. So when we solve the problems, we will get a better hold of it. Now, let us see the case of a saturated soil with no seepage. Okay, so this is the soil mass. The valve is closed here. You can see the water cannot flow out, so no seepage we are permitting. And the heads are all the things are given. So let us now write. Okay, first we will be attempting to write the total stress at each point. Okay, we will attempt to write the total stress at each point. So first we have the total stress, right? So at this point, what is the total stress? Which is 0. At this point, what is the total stress? H1 times gamma W. Now at this point, what is the total stress? H1 times gamma W plus Z times gamma set. This point, what is the total stress? H1 times gamma W plus H2 times gamma set. No, I've made a mistake. H1 plus H2 gamma W, right? This one plus H2 gamma set, isn't it? So if we want to compare with this, H into gamma W plus HA minus H times gamma set. HA minus H times gamma set. So yeah, I think this should be yeah, fine. So I am doing H1 plus H2 because you can see the pressure here is rising up, right? That's why I am writing H1 plus H2 gamma. Now the pore water pressure, the top You have 0. Then how much? Then we have h1 gamma w. Right. Then we have h1 plus z gamma w. Then at this point we have h1 plus h2 gamma w. So finally the effective stress 0, 0. Then what? Then h2 minus z. Sorry. Yeah. We have z, that is z. Sorry, z times the submerged. And at the end we have h2 times submerged. Okay. So then when there is no seepage. Now when there is seepage, let us see. When there is an upward seepage, so water is flowing from bottom to top. So at the top, what is the pore water pressure? That is the total stress. This point you have 0. Then we have h1 gamma w. Then we have h1 gamma w plus z into z, and in the end we have h1 plus h2. Yeah, this one, that's what I was thinking. Huh? This is h1 gamma w plus h2 z. Okay, so this one that's why I was confused. Yeah. Set. Pore water pressure 0. Now h1 plus z gamma w plus I to z w. I is nothing but this h by h2. This h by h2 I'm writing is I. I z gamma w. Okay. And finally we have h1 plus h2 plus h gamma w. Effective stress 0, 0. Then here at that here we have z gamma sub as I z w. Here we have h2 h gamma w. Okay. Now again this was upward. Now similarly for downward seepage. So here you can see this is for upward. So upward seepage at any point z, at any point z, at any point c, you can see here the effective stress is reduced by this amount. So this effective stress. So for no flow condition, this was my effective stress, right? This was my effective stress for no flow condition. But when if we have upward seepage, then my effective stress gets reduced by this term. It gets reduced by this term. Similarly, what will happen for upward flow? So as for upward, no, for downward page, the effective stress will increase. So again, here we have 0. Here we will have z comma sub plus I z comma w. Here we have minus. You will have here instead you will have a plus, and this will be nothing but h comma sub. Okay, this is also downward. Now this term, okay, this term is known as the seepage pressure. Okay, this comes from the seepage. If there is upward flow, the effective stress is going to reduce. If there is downward flow, the effective stress is going to increase. Okay. So when there is upward seepage, effective stress reduces. At critical hydraulic gradient, the effective stress is zero. At this stage, there is no contact between the soil grains. At critical hydraulic gradient, the effective stress is zero. Critical hydraulic gradient is nothing but submerged unit weight by unit weight of water. It mostly varies between 0.9 to 1. So effective stress, as you see, so when upward seepage is there, this is the effective stress. So when, if I equate it to 0, I will get I is equal to gamma sub by W. So my I critical is equal to gamma sub by gamma W is G minus 1 by 1 plus E. So this generally comes as 0.9 to 1.1. These are critical hydraulic gradient. So always we need to ensure that the critical hydraulic gradient is not achieved during for any hydraulic structure. Okay. So if a state comes that a critical hydraulic gradient is achieved, then what will happen? Effective stress will get to 0. That is, the soil will lose all its strength because there will be no intergranular contact between the soil particles, right? So the soil cannot take any more load. The seepage force is Iz our WA. A is nothing but the area. So seepage pressure times area is my seepage force. Seepage force per unit volume is given by this I into gamma W. We can get the hydraulic gradient from the flow net and thereby get the seepage force at any point, right? Hydraulic gradient and found on any flow net, and also you can hence get the seepage force. Factor of safety against heave can be calculated. Factor of safety against heave for sheet pile is given by submerged by I average by okay. So factor of safety is nothing but the weight by uplift pressure. So you say a sheet pile, here we have some head. Okay. So water will be flowing like this, right? So at the end point, what we do, so there is a chance of uplift. So uplift and the water to, that's in the soil to give up. Okay, there is this chance. So what we can do, we can put some soil mass over rock boulders or something over there. So that weight is given by W dash and U is the uplift pressure. Okay, the pressure with which the soil is trying to uplift the soil at that point. Okay, so we need to prevent that. So we push it down by providing, say, some boulders or something, put some weight. Use of filter in the downstream side to increase the factor of safety against heave. Minimum factor of safety of 4 to 5 is required. Filter allows flow of water through it but does not allow the soil grains to pass through it. Factor of safety calculation, factor of safety is gamma submerged filter by various criteria available to choose correct filter. So I'm not going into detail. You can see the class lectures. This is the first problem. So for the subsoil condition shown below, determine the total stress, neutral stress is the pore water pressure and the effective stress at all these points A, B, C, D. We need to determine the total stress, neutral stress, and the effective stress. So just try to do this. I'll be back in a minute. Just try to do it. It's very simple. Try to solve the problem. Right. So for the subsoil conditions, total stress. Okay. So first at the point A. So before we calculate, you can see E is given, S is given, 40 E is, that is the void ratio is given, saturation is given, and the G is given, right? G is the specific gravity of soil solids. Uh, So for the sand, first of all, let us calculate the unit weights. Okay, for the sand, first of all, let us calculate the unit weights. So what is the total unit weight? G plus S. We put the values. G you put 2.67, S you put 0.4, you put 0.5. Okay, gamma W you put 9.81. And you will get this as 18.77 the cube. And the gamma saturated can get what? G plus S1. S is 1, then saturated, right? G plus E, 1 plus E, gamma W. And we'll get this as right. Next, the clay water content is given, G is given. So E is what? Wg by S. Now, as the water table is here, the total soil is submerged, right? So S I can take as 1, so Wg, it will give me 1.08. So gamma saturated is G plus E, 1 plus E gamma W. Come out as 17.83 cube. Okay, so this we found out the unit weights. Now at A, what is the total stress? Is 0. At B, what is the total stress? This height, 3 meters times the total unit weight, right? So 3 times 18.77. What is the total stress at C? Is this 3 times 18.77 plus the this water, whatever water weight, that is 2 times the saturated, what is that? 2 times how much? 20.73 saturated unit weight, right? At D again, we have so this is what? This is 97.77. So D 97.77 plus how much? Plus 4 liters times the saturated clay, that is 17.83. Now it is 168.09 square. Now I will write the pore water pressures. The pore water pressure at A is 0. Pore water pressure at B is 0. Pore water pressure at C is 2 times 9.81 gamma W. Pressure at D is 6 times gamma W. So therefore, effective stress at A is total stress at A minus pore water pressure 0. D, this will come out as square square. All right, understood, right? Okay, fine. So total stress at A is 0, effective pore pressure is 0, total stress at B is 3 times the uh, unit weight of the sand. Then pore pressure is again 0, total stress at C is this the previous values plus 2 times the saturated unit weight of the sand. Okay, like this we find out the total stress, pore pressures, and then subtract it. So directly also you can calculate just the, if it's asked how to find the effective stress, directly you can calculate. So the submerged unit weight, if you want to calculate the effective stress at C, what will be the effective stress at C? Effective stress at C will be nothing but the 2 times the submerged unit weight of the sand. So what is the submerged unit weight of the sand? It's 20.73 minus 9.81. This is my submerged unit weight of the sand. These times the 2, this times 2 plus whatever the stress is at B. 3 into 0.7. So 78.15. So we are getting 78.1 directly. Simple problem. So now let's calculate solve for this problem. Irregular soil deposit 7-meter deep over impermeable layer. The groundwater table is 4 meters below the ground surface. The deposit has a zone of capillary rise of 1.2 meter and a saturation of 50%. Variation of total neutral and vertical deposit. You have to find out E is given, G is given. So this is the ground level. Then groundwater table is 4 meters below. 4 meters below. Here we have the groundwater table. The surface deposit a zone of capillary rise 1.2 meter with saturation this much. So 1.2 meter we have capillary zone. Rest of here this is the 7th level, right? 7 meter level. Here the soil is dry, and here at this portion it is saturated 50%. So S is equal to 50%. And this at this portion S is equal to 100%, right? Obviously 100%. So first let us find the dry unit weight. And moist unit weight. Now let us write this as A layer, B layer, C layer, D layer. Okay. Now at A, what is the total stress? Total stress is 0. What is the pore water pressure? Pore water pressure is 0. What is the effective stress? Effective stress is 0. At B, what is the total stress? 2 times the dry unit weight, 16.2. What is the pore water pressure? So now see, since there is a capillary rise, okay, since there is a capillary rise at this level, the pore water pressure will be negative. So minus 1.2 times the gamma W. Okay, and the effective stress 57. So 2 into 16.25 minus of minus 1.2 into 9.1. So it will get it up. So, and let's see. Let's see. We have 1.2 times 1.2. Let's see, right? Let's see, where is C? C is here. So at C, we have 4 minus 1.2. 2.8 times 16.25. 2.8 times 16.25 plus 2.8 times 16.25. 2.8 times 16.25 plus 1.2 times this moisture, 18.08. What is 67.6? This is 0. And effective stress is nothing but 67.6. At D. At D, first we have 2.8 times 16.25. 0.8 times 16.5 plus 1.2 times 18.08 plus 19.93 times 3. This will come out as 26.98. D is how much? 3 times gamma W. Okay. That's that square. Alright, I hope this is clear. Very simple. Just the tricky part is here, where there is the capillary action. Okay, capillary action. Our next problem. A soil sample, which is a sand, obtained from a trench has a water content of 38%. The specific gravity of solid is 2.65. Determine the critical hydraulic gradient for the soil. Also determine the maximum permissible upward gradient if a factor of safety of 3 is considered. Now, this is very simple, right? So critical hydraulic gradient, how to find? You already know. G minus 1 by 1 plus E. So just calculate this. I will wait for 1 minute. I want you to do it by yourself. So please try to do. Just put the value of G and E and find out the critical hydraulic gradient. So 0.822. Now, this is my critical hydroelectric gradient. Also determine the maximum permissible upward gradient if a factor of safety of 3 is considered. So maximum permissible is 0.822 by 3.274. So maximum this much upward gradient we can allow. Okay, considering for the factor of safety. Okay. Let us see the next question. A concrete gravity dam 120-meter long and 75-meter wide lies on permeable soil with a coefficient of permeability of 40 into 10 to the power minus 3 millimeters per second. The head of water is maintained at 32-meter upstream and 0 at the tail end. The soil is underlain by an impervious strata. The depth from the base of the dam to the impervious strata is 38 meters. A flow net constructed for this condition yielded 8 flow channel and 18 equipotential drops. What is the seepage loss per day under the dam considering a 2D flow? So this is very easy. Everything is given in the question. That we already discussed it in the previous class. Also, we discussed this concept. This class also we discussed, right? Previous session also we discussed. This session also discussed. So you should be able to solve it. It's very easy. Everything is given. Just do it. Try to solve. Try to solve. Sorry. Just try to solve. Try to solve this. Very easy. Everything is given to you. Q. The what seepage loss you need to find out. All the other required information are given in the question. Directly just using one relation, you need to calculate this. It's very easy. Do it, please. It's very easy. So what are the how many number of flow lines it's given? It's given number of flow channels are 8. 8 number of flow channels. Number of drops 18. It's given the head of water, so concrete gravity dam, right? Maybe like this. Yeah. Yes, the head of water is maintained at 32 meters in the upstream. So if this is water head, this is 2 meters. And yeah, and this is again impermeable is given as 8 meters. Okay. So number of flow channels is given as 8, number of equatorial drops is given as 18. So here this condition is directly given to you. Actually, in reality, what you need to do is that in reality, with the information, so you forget about this information. Think that this information is not given to you. Then what we need to do? Then you need to draw this thing with proper scale in your paper. Okay, in a paper, and then construct by hand the flow channels. Okay, construct by hand the flow line, the flow net, the flow line and the equipotential lines. Okay, you need to construct by hand and then check whether this is right or not. So this I suggest you do by yourself. I give I suggest you do this as your home task. You take a piece of paper, a piece of chart paper or paper graph paper, you plot, you draw this figure with the help of a proper scale. In proper scale, draw everything and see how you need to draw flow net. Take the help of the internet or the standard books. Okay, the class notes. Okay, and then you draw the flow net by yourself. You draw the construct the flow net by yourself, and then you calculate the flow and you check whether you are getting the same amount of flow or not. Okay, you do this yourself one. Here directly the values of the flow net are given at 8 flow channels, 18 equipotential drops. But you do this yourself once by draw by hand and check whether how many drops, how many you are getting this the same flow net or not. Okay, you do this by yourself. Okay, it's given which is nothing but 14 minus 3 by 1000 to meters per second. Right, so 40 into 10. Now, what is the total head? Total head is 32 meters, right? Total head is 32 meters. Initial head. Now, what is Q? KH, number of flow channels by number of equipotential drops. 40 into 10 to the power minus 6 times 32 times 8 by 18. Okay. So it's asked, what is the seepage loss per day? So these units we need to do some conversion. 32 it's meter, let's be meter per second. I have to convert to second. So this will be 60 to 60 to 4. So it will come out as 49.152 meter cube per day per meter. Excuse me, per meter length of the dam. Okay. Okay, see whether you're getting it or not. Okay, draw the flow channels, flow net, everything by yourself, and then you are check once whether you are getting this or not. Okay. All right. Ah, sorry, this cold is like Taking the hell out of me. Sorry for the inconvenience, huh? Okay, now let us see the next problem. Similar problem. Okay, try to do this. This is the same problem. Almost same. An earth dam is built on an impervious foundation with a horizontal filter at the base near the top. The permeability of the soil in the horizontal and the vertical directions are given 3.2 to the power minus 2 mm per second and 1.5. The full reservoir level is 30 meters above the filter. The flow net constructed for the transform section of the dam. So see, it's written flow net constructed for the transform section of the dam. So you can understand, right? So again, as I said here, it's a case of anisotropic soil. The kx and the k vertical and the k horizontal are different. The hydraulic conductivity in the horizontal and the vertical directions are different. So you need to use the transformation that we discussed. So see, so this one also I suggest you do it by yourself. To take the scales, you draw the flow net properly. Okay, see the step by see in the textbooks how you have to draw the flow net for this impervious case. Okay. Plot is constructed for the transform section of the dam consists of 5 flow channels. Certain point it's given to you, but I suggest you do this directly for us solve the solution purposes. Everything is given to you, but I suggest you draw this in a piece of paper and draw the flow net yourself. Then you will learn. Estimate the seepage loss per meter length of the ground. All right. So do this. Everything is given again directly. Just you need to calculate. It's very easy. Do this please. Very same na. Directly just you have to use the values that is given to you. Yes. And it is how much? 5, 10 is h. So q is what? Root over kx times kz h by d square root 3. So calculate. So how much are you getting? 2.8. You check these values yourselves. Okay, do these problems again by yourself and check the results. Okay, per meter. Okay, next one. Calculate seepage flow per meter length of the dam if coefficient of permeability is this much. Okay, first we have to calculate the seepage flow. Same as the previous problems, we will use the values from these to calculate the seepage flow. Calculate uplift pressure along the base of the dam, compute the exit gradient and factor of safety against boiling if the elementary square at the top of the dam has been measured to have dimensions of 2 meter, 2.4 meter. The elementary square here at the end of the dam, it's all the dimensions of 2.4 meter. Use unit weight of water as 10 kilonewton per meter. Okay. Okay, so we have a concrete dam and here we have a sheet pile type thing structure also we have here. Okay, first we are asked to calculate the seepage flow. Seepage flow, same relation, whatever we used in the previous problem, same thing we have to do, right? Same thing we have to do. So what is our H here? What is my H here? Total head. So that is 6 meters. So that is 6 meters. Now NF, total number of flow channels. We count total number of flow channels. We have one, 2 here, and then we have this 3. So 3 number of flow channels. The total number of drops 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 number of drops we have. Okay, so 3 flow channels and 10 number of drops we have, right? The is 10. And our K is given as 1.5 into 10 to the power minus 4, isn't it? Yes. Now what is Q? What is Q? Q is a cubic meter per second. Yeah. Okay. So what more are we asked? Calculate the uplift pressure. Okay, we'll calculate the uplift pressure after we calculate the other part. Okay, compute the exit gradient and the factor of safety against boiling. The elementary square at the toe of the dam has been measured to a dimension of 2. Let us do this part first. Now, what is the exit gradient? Exit gradient is the gradient here when the water is exiting at this part. The gradient is my exit gradient. Now, what is the hydraulic gradient? What is the formula for hydraulic gradient? Is nothing but hydraulic gradient is the head loss by the length of flow. So the head loss from here to here divided by this length should give me the Give me the what? The head loss from here to here, from here to here, divided by this length. This length should give me the exit gradient. Now, exit gradient is what? Head loss by L. What is the head loss? Total head divided by the number of drops will give me the head, what to say? The head lost in each drop. The head lost in each drop. So that will be the head loss there, right? So 6 is the total head number, the total number of drops 10. So that will be that is nothing but that is the head lost when the flow from here to here when the flow is happening, right? Divided by L, length of flow is what? 2.4. So if I do this, the exit gradient will come out like 0.25. Now, generally the critical hydraulic gradient, we saw it before, that is generally between 0.9 to 1.1. 0.9 to 1.1. It's generally between 0.9 to 1.1. Now, say my critical hydraulic gradient is 1. Then what is my vector of safety? 1 divided by exit gradient is less than that. So 4. So my factor of safety is 4. Okay. Factor of safety is 4. Alright. Alright. Now we need to find the uplift pressure at all these points A, B, C, D, E, F. Okay, all these points we will calculate the uplift pressure. The uplift pressure. For that, we will make a simple table so that it will be easier for us. So first we have number of drops. Then we have total head. So what will be the total head? Total head at that point. I remember total head at any point. Total head at any point A is what? The initial head minus the number of drops at that point times the head lost in each drop, right? So total head is equal to nothing, will be nothing but 6 minus drops times 6 by 10. Okay, this way we will calculate the total head. Then we have the elevation head. So the elevation, my datum I will consider as this level, round level I will consider as the datum is given here. See. And then finally we have the pressure head. Right, pressure head is total head minus elevation head, and finally you have the pressure. Uplift pressure is nothing but the pressure head times the gamma w. Right, at point A we have the number of drops. So A is where? A is somewhere here. Okay, here means from here to here it's 1 drop, so we can say 0.5 drops approx here up at this point. The number of drops is 0.5. So this will be 6 minus 0.5 into 6 by 10, 5.7. Elevation head is minus 1. Pressure head is elevation head minus 1, right? Because it's here it's given 1, so it's 1 meter below the datum, so minus 1. And we have the pressure. So A point, A is written here, but it's actually kind of here. Okay, it's here at this point. This point A is there. A is here. Pressure head 5 minus 7, 6.7. Uplift pressure is 67. Gamma W is they have asked us to consider as stand. Then B, number of drops 1, 1, 2, 3, 4. Here, so here B is here, right? So 4.5, approximately 4.5. 3.3. Let's see. 5 drops. See this one. 4, 3, B, 6. Sorry, no, not 2.4. What am I writing? 2.4 will is this one. Right. This is number of drops's 6. 3.4 minus 1, 3.4. 4. Then E 7 drops, 1.8. 28. Finally F, we have 8 drops. 0.2 minus 1, 2, 22. Okay. Parameters. So this is the uplift pressure. Okay, like this you need to calculate. Okay. Now the last problem for today's session. Two rows of sheet pile are driven to a depth of 4 meters. So one more before if we go. So this sheet pile here or some this structure is given here so that the flow path, the length actually increases. Okay, the length of flow increases. The length of flow will increase the I by L. Right, I already did this H by L. The exit gradients will become lower. That's why we give this to increase the length of flow. Also, one more thing, because see, if you do not give this here, the flows will be like this, like this, like so. Higher applet pressure will be there. But with this, we reduce the applet pressure also. Right? Because by increasing the flow path, we reduce the applet pressure. So, lift pressure, yeah. Understood, right? So if this was not there, maybe less number of drops. So now the for the water to reach from here to the point C, we have to encounter 5 number of drops, equipotential drops. But maybe if this was not there, the path would have been shorter, right? The path of flow would have been shorter, then lesser number of drops would have been there. So higher apply pressure would have been there, right? Yeah. That's the last one. Two rows of sheet pile are driven to a depth of 4.4 meters below the bed of a river to form a cofferdam. From a cofferdam, excavation is then carried out within the cofferdam up to a depth of 3.3 meter below water level by keeping the area free from water by pumping. Riverbed is sand with hydroconductivity conductivity or coefficient of permeability is 3 into 10 to the power minus 3 centimeter per second and is underlain by an impermeable stratum at depth of 6 meter below the riverbed. What is the quantity of flow into the cofferdam per hour per meter length of the sheet pile walls? Is there any danger of quicksand? So cofferdam is nothing but this. So two sheet piles are driven into the soil and the water is excavated out from here, pumped out from there. No, excavated is the wrong word. It's water is soil is excavated out and water is also pumped out. Okay, water is pumped out and then soil is excavated out. Okay, so this so maybe to do some construction in this part, we need to we first install the sheet piles, then pump out the water and then excavate the soil. All right. All right. So it is asked what is the quantity of flow into the coffer dam. Okay. So we need to find out how much water is in flowing into the dam. Okay. From this side and this side, both the sides, how much water is flowing. The same, we will use the same fundamentals that we have studied. So I will erase this, huh? U is KH and F ND. Now K is 3 into 10 to the power minus 3. Okay, into 10 to the power minus 2. I convert it to meters, centimeter to meter. H is 1 point. H is how much? H is not 1.8, it is 3.3. At this level, the hair high is 3.3 to NF by ND. So now how many flow channels? 1, 2, 3, and from this side also 1, 2, 3. Total 6. 6. A number of drops: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 number of drops. 11 number of drops. Okay, 11 number of drops. So it will come out as 5.44 into 10 to the power minus 5 meter cube per second per meter length of the tank. Okay. Now next is, what is the quantity of flow if 100? Right? Then is there any danger of quicksand condition developing at the bottom of the excavation? I get this part. But this part for the this length is given for this flow channel, last length, exit length 0.65. Now I will find out the exit gradient again. What? Total head is 3.3, lost in 11 drops. Similar to that problem. Okay, divided by 0.65. So this complete is my what? Is the head H. Okay, 5.65. This is the head mean lost in per drop. How much head is lost in each drop? At 5.65 is nothing but the length of flow. What is 0.4. Similarly, if you take I critical as 1, the factor of safety, if I critical as 1, then factor of safety 1 by 0.42 is 2.38. So 2.38, it's safe, but we require it's suggested that it's always preferred that the factor of safety is little bit higher, more than 3, 4 like that. Okay. Okay. So I hope everything was clear to you. So with this problem, we will end today's session. Okay, so we solved very simple problems. I don't think you should have much difficulty in understanding or solving this by yourself also. All right, so very easy, simple problems. All right, and the 6th week discussion session will be on the Monday, coming Monday, this 24th, but the time will be same as today, 4 p.m. to 6 p.m. Okay, 4 p.m. to 6 p.m. on Monday. Okay, this Monday, 4 p.m. to 6 p.m. 24th of February, Monday, 4 p.m. to 6 p.m. 4 p.m. to 6 p.m. Okay. Okay, Monday, 24th February, 4 p.m. to 6 p.m. We'll have the next discussion for the 6th week. Okay, 6th week discussion session. Okay, so thank you so much for attending today. See you in the next session and have a very good evening. Okay, thank you. So if you have any doubt, you can ask me. I am here till 5 more minutes. If you have any doubt, you can ask me or you can leave. Okay, thank you. Thank you so much for attending.